Alright, hello and welcome to the OneClass Popular Math Questions. My name is Richard and today we're going to be going over 10 questions. If you require any more help or tutoring, please be sure to check out the links in the description below. So, with that being said, let's get to our problem set for today. Alright, so first question, number 1. If a polynomial function f of x has roots 3 and root 7, what must also be a root of f of x? So we have to understand what having roots of 3 and root 7 mean. Basically, this means that our polynomial can be written as the product of certain factors, right? So let's say you have roots a and b of a quadratic equation, for example, right? And we know that a quadratic equation is some equation in the form of um, let's use different letters, ex squared plus fx plus g, right? And we know that we can possibly factor this into the product of two terms if we have two roots. So with that being said, ultimately, if this equation has roots a and b, then we can write it as x minus a times x minus b. And this would still be the same equation, but now it's written in a factorized form. So essentially what this means is that our polynomial function having roots 3 and root 7 can also be written as the product of x minus 3 because that's one of the roots. And then because we are dealing with a root 7 here, right? This essentially means that our second term would have to be x squared minus 7, right? Because when we set this equal to 0 and actually find what our roots are, plugging in root 7 into here would give us 7 minus 7, which then gives us 0. So this is basically our factorized form of our polynomial function, f of x. And what the question is asking is what must also be a root of f of x. So we know that 3 is definitely a root of this term resulting from this term. What we also can realize right here is that whether we plug in positive or negative root 7, this term still becomes 7 minus 7 at the end of the day. So with that realization, we could say that our third root is negative 7. So that must also, as a consequence to positive root 7 being one of our roots, minus the square root of 7 is also one of our roots. So this is what the answer would be for this question. And let me just check what has been done here. And yeah, this is essentially the same thing here, a little bit more of shorthand. I went into more detail, so this is correct. Great job. And with that being said, we can move on to the second question. Okay, so here we are now dealing with number 2. And number 2 says, which polynomial is a perfect square trinomial? And we are given 4 answer choices, and we have to select the ones that are perfect square trinomials. Now, first we have to define what a perfect square trinomial is. And a perfect square trinomial is something that can be written either as a minus b quantity squared or a plus b quantity squared. So if any of our trinomials can be written in either one of these forms, that means it's a perfect square trinomial. So that's essentially what we're going to be looking at, going through these answer choices. So for the first answer choice, we're going to have 49x squared minus 28x plus 16. And I have to actually be more specific here. So dealing with trinomials, this is going to be of the form ax minus b and ax plus b. So with a quick glance here, we could realize that our a in all of these questions is essentially going to be the square root of the coefficient that is in front of the quadratic term. And that's because when we actually multiply out any one of these terms, our first, um, so let me just expand on ax minus b, for example. So we get a squared x squared minus 2abx plus b squared. And then the same would happen for here, but instead of a minus, we have a plus here. So a squared x squared plus 2abx plus b squared. So with this realization, we have to set our a right here, our a to be the square root of this number here. So the square root of 49 is 7. So we're going to take our a to be 7. Now, going along here, because this is of the form, we already realized that we are going to be using the a squared x squared minus 2abx plus b squared form, because it closely resembles the signs of this first answer choice. So because we have our a, we have to now find what our b is. So substituting a for 7, we have minus 14bx, and now we know that the value of b that completes this would be b equals 2. So far so good. These first two terms line up with our assumptions, but now when we get to this third term, this term has to be equal to b squared. And in our case, since our assumption that b is 2, b squared is going to be 4, which is not equal to 16. So therefore, this is not a perfect square trinomial. Okay? So it went against our assumption. So that means our assumption was false, and therefore it can't be factored into a perfect square trinomial. And this answer choice and this written answer also says the same thing. So going to the second answer choice, we have 4a squared minus 20a plus 25. And right here, we have to set our a once again equal to the square root of this coefficient. So a is equal to 2. And then, because we're dealing with a minus plus situation, we have to find what b is. So in this case, it would be minus 2 times a. A is 2, so minus 4b equals 20. In this case, b would be 5. And let's check if our assumption is correct. So this term has to be b squared over here. And because in this case b squared is 5 squared, which is 25, everything checks out, our assumptions check out, and we can write this trinomial as a perfect square trinomial using this ax minus b quantity squared representation. So we can actually write this as 2x minus 5 squared using the same form of a perfect square trinomial. So with that being said, this would be, so this is perfect square trinomial. And now we can move on to third answer choice. Our third answer choice here is 25b squared minus 20b minus 16. So because we are dealing with, so essentially, we can once again go through the assumptions. So we're going to say that in this case, the square root of 25 is going to be 5. So our a value is 5. And then right here, this would mean that minus 2 times 5b is equal to 20, meaning that our b value, sorry, minus 20, so our b value would be 2. However, assuming that our b value is 2, we get b squared is equal to 2 squared equals 4, which is not 16. So this is not a perfect square trinomial. Okay? And then the fourth answer choice here, we get 16x squared minus 24x minus 9. And once again, the square root of 16 is a equals 4. And then we're going to have minus 2 times 4b has to be minus 24. So minus 2 times 4 is 8. So that means that b has to be 3 in this case. And here our assumption does hold true because b squared is equal to 3 squared is equal to 9. So that means that this equation, um, this even though this equation does have an a and does have a b solution, the fact of the matter is, when we look at the two forms that we could possibly have a perfect square trinomial in, we see that that neither one of these forms can be met because there are two minus signs right here. And also, um, really, b squared equals 3 squared has to equal to negative 9 because we do have to consider the sign here. So ultimately, we would assume that it could be factored, but because of the signs, it actually can't be factored. So we say that it is not a perfect squared trinomial. Okay, so in that case, the correct answer choice is answer choice 2, and this written response here does a good job at showing that. They are using the complete the square method. I tried to take what I consider to be a more simpler approach. So I'm going to write this as the correct solution. Good job. And that is number 2. Okay, so for number 3, we just have remote interior angles. So I'm guessing going over the concept of remote interior angles. So I'm going to use this diagram right here because I feel like it's a good one. I'm just going to draw it out here, and we're going to have point D, C, A, and B, and then we're going to have, so because the way that the naming convention goes for angles should be the lowercase. Okay, I'm just going to be consistent with the diagram here, so the naming convention might be a little strange, but let's 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 be consistent here. So ultimately what we say is that because we have this triangle right here, and because this angle on the outside of the triangle is formed by this horizontal ray, we say that angle D, so I'm going to write angle D, Okay, so it turned out that my audio was cut off for what I'm assuming to be that last question. That is my fault. I will continue on, but in any case, that's not ideal. So number 4, how many nickels are there in $17? So if we think about $17, we have to first think about how many nickels are in $1. So if you have $1 and the value of a nickel is equal to 5 cents. So how do you find how many nickels are in a dollar? Basically, you want to find the number when you multiply by 5 cents, you get a dollar. One way of doing that is you could just divide the two, and then we can move both numbers by 2 decimal places as a property of division in order to get the denominator to be a whole number. So this is the same thing as 100 divided by 5, and we get 20 nickels. So because we have 20 nickels in $1, so 20, I'm going to use N to denote a nickel, and I'm going to use a D to denote a dollar. 20 nickels in a dollar. We want to see X nickels in $17. By cross multiplying this proportion, we get 340 equals X, so 340 nickels. The easy way would just be multiply 17 by 20. This proportion weighs a little extra, but ultimately that is how many nickels that we get in $17. And this answer choice here is correct. So I will say this is the correct solution. Great job. Okay. And on to number 5. So for number 5, we have to find the integral of cosecant of x dx. Okay, so some calculus here. The first thing that we have to do, so this isn't intuitive, solving this integral. So the first step, you have to multiply this integral by a certain fraction, and that fraction is the cosecant of x plus cotangent of x over cosecant of x plus cotangent of x. And the reason why we can do this is because ultimately this is just equal to 1. So we're going to do some manipulation here because our numerator and our denominator is the same here. We can do some manipulation. It's the same as multiplying by 1. So the next line we would get here, we have to utilize the u sub. So we're going to let u equal, oh, I'm sorry, we should probably, no, we could use the u sub right now. So we're going to let u equal to the cosecant of x plus cotangent of x. And then we're going to have du equal, so when you take the derivative of the cosecant of x, you get negative cosecant x cotangent x. And when you take the derivative of cotangent of x, you get minus cosecant squared x dx. Okay? And then with that being said, we can ultimately plug this in as dx being equal to du over this term here. Okay. Now going back to the integral, I probably should have multiplied these out here. So let's multiply this cosecant x into the numerator. So we get the integral of cosecant of squared x plus cosecant x cotangent x. That's what happens when we multiply in over our denominator. Okay. And then we're going to substitute in for dx here. So plugging it in, we get du over, and then I'm going to get rid of this minus sign from inside of this term in order to make it look like our numerator. So we're going to have cosecant x cotan x plus cosecant squared x. Okay. And now, one more thing that I did not do here is because I'm doing the du, substituting in du instead of dx, this cosecant x plus cotangent x is actually a u, so I'm going to plug in a u here. Now, the numerator and denominator cancel. We can't forget about this minus sign here, so we're going to take it out, and we're just going to get minus integral of 1 over u du. And now this is very easy. The integral of 1 over u is just the natural log of u, so we're going to get minus ln of u. And then we could just substitute in for our u, and we defined our u to be cosecant x plus cotangent x. So ultimately this means that we're going to get minus ln, want to use the absolute value bars because we can only take the ln of a positive number, of cosecant of x plus cotangent of x. And this would be our answer. Oh, and because we are dealing with an indefinite integral, that was a rookie mistake by me, we have to add the plus c always. So always indefinite integrals, you want to have that constant. And that would be the answer. So that's correct. And I'm going to say this is the correct solution. Great job. Okay. All right. So moving on to what number is this? Number 6. I got thrown off by this number 5 right here. I knew it was number 6. And we're going to evaluate the following limits. So we have this image here, okay, and this is the limit that we have to evaluate. And there's nothing else, right? Okay. So I'm just going to copy this over. So we have the limit as x goes to 1 over 4 of 1 minus 4x over the square root of x minus 2x. Okay. So what do we know about limits? The first thing we could try to do is we can just plug in what we are evaluating the limit at. So let's try plugging it in. So if we get 1 minus 4 times 1 over 4 over the square root of 1 over 4 minus 2 times 1 over 4, we end up getting 1 minus 1 over 1 half minus 1 half, and we get the classic 0 over 0 case. Now, what's good about the 0 over 0 case is that if both the numerator and denominator are differentiable and we have this 0 over 0 case, we can use L'Hopital's rule. So the condition is we have to get that undefined 0 over 0, plugging in the value at which we're taking our limit, and you have to be able to differentiate the top and bottom. So we can differentiate the top and the bottom, the numerator and the denominator, and what we end up getting is the limit as x approaches 1/4 of minus 4, because derivative of a constant is 0, derivative of minus 4x is minus 4, over, we can write this as x to the 1/2 power, so taking the derivative would be 1/2 x to the minus 1/2. And then we get minus 2, derivative of minus 2x is minus 2. So this is actually, I'm going to write this x to the minus 1/2 as 1 over square root of x, and then minus 2. Now we could see if we could plug in our 1/4 into this and actually get either a truly undefined, or a truly limit does not exist if we have a constant over 0, or any other value. So let's try plugging it in. So we get minus 4 as a constant on top, over 1/2 times 1 over square root of 1/4 minus 2. And this is going to give us minus 4 over, so the square root of 1/4 gives us a half. 1 over a half is 2. 2 times 1/2 is 1 minus 2, which is minus 4 over minus 1, which is 4. So because we were able to evaluate this limit, after L'Hopital's rule, excuse me, we found that our limit is equal to 4. So um, I'm just going to write that in here. So after using L'Hopital's rule once and substituting in for x equals 1/4, we find that the limit evaluates to 4. Good suggestion for L'Hopital's. Okay. And that would be sort of correct. Okay, so we just finished number 6, and we are starting number 7. Okay, so for number 7, we have this question: what is the following product? I don't see any product here. I am going to assume this is the product we're talking about, this square root of 12 plus square root of 6 times square root of 6 minus square root of 10. So I'm going to assume this is the product and go about it this way. So we have to use FOIL, and whenever we use FOIL, just as a rundown, if we have any a plus b times any c plus d, we want to multiply first inner, so we want to go a times c plus a times d plus b times c plus b times d. And that's basically how a FOIL of terms with sum of two terms, the product of the sum of two terms, is carried out. So with that being said, let's carry this out on our problem here. So we're going to have the square root of 12 plus the square root of 6. And another thing to note, that whenever we have the square root of a times the square root of b, we can actually bring them inside of the square root as so. So we have the square root of ab. And that's what we're going to do for all these products. So we're going to have the square root of 12 times the square root of 6. I'm going to write them out separately initially. So that's the first one, and then minus the square root of 12 times the square root of 10, and then plus the square root of 6 times the square root of 6 right here, and then plus the square root of 6 times the square root of 10. And now by just bringing them in together as products inside of their respective square roots, we're going to have the square root of 72 minus the square root of 120 plus the square root of 36 plus the square root of 60. Now, in order to actually begin to evaluate these and see if we can combine anything, we have to simplify these radicals. So the way it works is we're going to factorize them, we're going to prime factorize them, and see if we can get them as the product of two square roots where one of them is a perfect square. So just off the top of my head, I know that 4 goes in, I know that 9 goes into 72. So that could be written as the square root of 9 times the square root of 8. Another thing is I can possibly see this being written as the square root of 4 times the square root of 30. And then square root of 36 is easy because it's a perfect square. So we're going to have 6. And once again, I can see the square root of 60 being written as the square root of 4 times the square root of 15. So after this first step here, we're going to get, so the square root of 9 simplifies to 3, square root of 8, and just to save another step, let's see if the square root of 8 can be simplified further. I know it can be. It could be broken up into the square root of 4 times the square root of 2, where 4 is our perfect square. And then we're going to get minus 2, and looking at this square root of 30, there's not much we can do with it to actually decompose it because none of its factors are perfect squares. So then plus 6 plus square root of 4 is 2 square root of 15. So After this final step here where we just evaluate the square root of 4 and multiply it to 3, we're going to get 3 times 2, which is 6, root 2 minus 2 root 30 plus 6 plus 2 root 15. And this is our answer right here. And it is said exactly the same way here. So option A, if that is what option A is, that is correct. So this is the correct solution. Great job. And got an extra space here. Okay. And that would be correct in this case. So time for the next question. Okay, so how many unique ways are there to arrange the letters in the word pretty? So, pretty. First thing to notice is how many letters are in the word pretty. So we have 6 letters. The next thing that we can do is we can come up with all the possible scenarios of arrangements for this word. So we know that there's 6 different spots that could possibly be filled in because we have 6 letters. And for the first spot, we have the choice of all 6 letters to go in this spot, right? So right here, there are 6 different letters that can go in the spot. So let's assume now for the second spot, we use the letter P. So letter P is gone. In this case, that we have 5 letters left that can go in this spot. No matter what letter we've used, once it's filled into the first spot, we will always have 5 letters here that could be filled in here. And then once again, let's assume we get rid of R. We only have 4 letters left, so we can continue this trend here and see that these are the number of letters that could be filled into each spot once the previous spot has been filled. And by multiplying all of these possible arrangements, we actually get what the total number of possible arrangements is. So 6 times 5 is 30, 30 times 4 is 120, 120 times 3 is 360, 360 times 2 is 720, anything times 1 is itself, so we get 720 different arrangements. And that would be our answer for this question. So I'm going to write this is the correct solution. Great job. And that is the end of this question. Okay. So, question number, sorry, must look at the previous one. 7. Okay, we are in 8. So question number 8. First, okay, 16 divided by 3, simple enough. So what happens if we were to actually long divide 16 divided by 3? I feel like this is not the best way to initially explain it, but we can kind of see what happens here. So dividing 16 by 3, first we could put a 5 up here, 15, get a 1, we have to add a 0, and then afterwards, actually let's just go with this route. So we get a remainder of 1 here. So 16 over 3 is equal to 5 remainder 1. And normally what we do with our remainder is we can write our remainder over our divisor. So in this case, 3 is our divisor, and 16 is our dividend. Okay, yep, dividend. And we can actually write this as 1 over our divisor, because that's just how remainders work in division. So we get 5 and 1 over 3. Okay, so this is the mixed number way of writing it, the whole number and the whole number and fraction method, so 5 1/3. With that being said, we can't actually write it in decimal form. The way to write it in decimal form would just be 5.3 bar, because as I wanted to show up here, if we kept carrying on this division, we would keep getting 0.3333 because we would always get a remainder 1 going out whenever we carried out the division. So 5.3 bar is another way to look at this. And if we want to verify that 5 1/3 is actually correct, how you normally convert mixed numbers to impartial fractions is you would multiply the denominator and the whole number and add the numerator and put it over the denominator. Our denominator down here, we get 5 times 3 plus 1, so you get 16 over 3. And that is what we had. That's the same thing as 16 divided by 3 in impartial fractions form. So that's how we know that 5 1/3 is the correct answer. And here it's done the same way. So this is the correct solution. Great job. Okay, and that concludes number 8. All right, so number 9. We have a few images to open here. So let's go through them. So these are just the questions, and this is the actual graph we're going to be working with. So I could probably do this. Yeah, this works. Is there a B? No, there's no B. Okay, so we have to, let me just rearrange this. Yeah, this looks a lot nicer. Okay, so dealing with question A. So first, let f be the function with domain 0, 6, given by the graph below. List the critical points of f on the interval. Write none if appropriate. Okay, so basically, the critical points of this graph would be the points where we want to see where we have a maximum. So, or not necessarily a maximum, but where our derivative at that point is. So hold on. So a critical point means that our derivative is 0 or undefined. Okay. So having a derivative of 0 or undefined. So that means that f prime is equal to 0 or undefined. So looking at this graph, we first have to find points that are differentiable. And points that are differentiable normally have to be continuous. So we can rule out some of these points. We could rule out these points, this point, and this point right here. The other point that comes to mind, so whenever we think of anything with a derivative of 0 or being undefined, we either think of maxima and minima, so this point and this point, where the derivative is 0, meaning that this tangent line that we can draw is perfectly horizontal, the slope of the tangent line is 0, or where, let's say we have a point like this, so where it is a maxima or a minima, but because there are so many ways that you can draw a tangent line, we have undefined undefined derivative. So right here we see that this point, so at x equals 4 is one critical point, and that's really the only other point. So to be more specific, it's 4, 1. And this point right here is called an inflection point. An inflection point meaning that this is where the derivative changes from being negative to positive. So if we consider this inflection point right here, then we see that derivative is decreasing, decreasing, decreasing. So it is increasing slower and the second derivative at this point is 0. So for that reason, it's not a critical point. The first derivative is changing, meaning that the second derivative is 0 at this point. So we do not call it a critical point. So our only critical point is at 4, 1 right here. So I apologize for if it's a little messy here, but moving on to question B. So we want to, oh, my bad. Okay, let's just do this. Let's shrink this. And we're gonna list the inflection point. Okay, so as I was just talking about, so the inflection point is where normally an inflection point looks something like this. So this point right here. And the reasoning behind it is that let's say everything on the left of this point, we know that the derivative is positive because, or that the, we know that the function is increasing, right, on the left side here of this interval. But it's the rate at which it's increasing is decreasing. So because of this curve right here, we see that it is steeper here and it's less steep over here. So that means that the second derivative, or the second derivative is how the first derivative is changing, is basically decreasing. Then when we get to this point, the first derivative is not changing. Because the first derivative is not changing, we say that f double prime of x is 0. Past this point, it goes from being less steep to more steep. And that means that the second derivative is increasing. So an inflection point, an IP, is this point right here, where the second derivative is 0. And we see that the only point where that happens is at 3, 0, as discussed also previously in part A. So now part C is list the intervals on which f prime is negative. Use the graph. Okay. So f prime is negative. So what does f prime of x being less than 0, another way to say it's negative, mean? That means that the slope is negative. So that implies that the function is decreasing. So the function is decreasing. So let's have a look at where the slope is negative, or the function is decreasing. So right here it's increasing, if you follow my mouse, increasing to this point, and then increasing over here, increasing. It's increasing less, but it's still increasing. Then it's increasing, and then past 4, so from 4 to 6, the function is decreasing, meaning that its slope is negative. So we say that this would be at the interval 4 to 6. And we should probably not actually include 4. Or possibly any of them. So I'm just gonna say 4 to 6 right here. So this interval right here. Now for part D, we're gonna see the interval on which f prime is decreasing. So f prime decreasing, is the same thing as the second derivative, because the second derivative is basically f prime of x prime being negative. So that means that the function is that the rate at which it is decreasing, or the rate at which it is increasing, is going down. So let's examine our intervals. So here the function goes from being less steep to more, so meaning that f double prime, if anything, is increasing. Now from this interval 2 to 3 is our prime suspect here, because we see that the function goes from increasing to increasing less, meaning that its derivative is decreasing. So from 2 to 3, this is definitely our prime candidate. Going from here, it's increasing less, but then it increases more, and then it's decreasing less, but then it starts decreasing more. So f double prime is actually f double prime is greater than 0 here, and here it is only less than 0 from the interval 2 to 3. So I'd say 2 to 3 is our answer here. And list the x coordinates at which f prime has a local minimum. So local minimums can occur at, so in here, I'd say in terms of, so when we talk about a global minimum, we can easily say that our global minimum for this function is at 2 comma negative 1, because it is where our function has its smallest value for this domain. In terms of local minimum, we can say that the global minimum is a local minimum, so that makes it a candidate. And another, what I'm wondering here is if we were to consider I don't believe that we would actually consider these points to be minimum here. So in this case, I would just keep it at 2 negative 1 as our minimum. So that is that for this question. And then I'm just going to write some notes here because there wasn't actually an answer given. So I'm going to write reasoning and answer makes sense, but no direct answers provided. So we're going to have part A, CP at 4 comma 1. Part B, we're going to have our IP at 3, 0. Part C, we're going to have our domain B 4 comma 6. Part D, we're going to have our domain B 2 comma 3, and say that the minimalize at 0.2 comma 1. So I'm going to also write that. Okay. And that is the solution right here. So on to the next question. Oh, there is no next question. So I believe that is it. I must have miscounted somewhere here. So that concludes this stream. Once again, if you have any more questions, be sure to check out the links in the description for tutoring and any more homework help. This has been Richard, and I'm signing off. Have a great rest of your day, and